Hello and welcome to the Physics 2212 Lab 1 charged tapes. So our table of contents just showing us what we're going to be going through. And let's start with it. So the introduction. So the purpose of this lab was to observe and study the interactions of two charged pieces of tape and then create a computational model and compare this to our real-world observations and calculations where we would calculate the values of force and charge for the pieces of tape. Those are physics principles are Newton's second law and Coulomb's law. And then the outcome in this one is that we found the magnitude of the electrical force of the tape to be equal to the gravitational force, and that the tape was positively charged and had an electron deficiency of that number right there, which I'll show you those calculations later. So the main principles are Newton's second law, which is just F net equals ma. Pretty simple, just the momentum is proportional to the force applied. And then describes the force of attraction, that's Coulomb's law, and repulsion between different electric charges. So that's where we're going to end up solving for Q later. So these were our initial conditions. The tape length, tape width, and tape area are all pretty much given to you, along with tape mass and atom area. The only thing that you kind of have to calculate this initial condition is the number of atoms, which is your tape area, and you divide it by the atom area. And there you go. And then we know this is positive because we had a pencil that we rubbed in our hair, became negatively charged, and the tape was attracted to it. So this is our actual experiment right here. That's the video of it. So the system is tape B, which is the one on the top, as you can see from the diagram below the video. And then our surroundings are tape A and everything else. And then the distance we measured between them was 0.03 meters or 3 centimeters. So we use this in our calculations. So first, gravitational force, we know this because we know G, and we know the mass of the tape, and we know it's going downward. So it's negative. And we know the electric force is just going to match this, but in the positive direction, in the opposite direction. So we have that. To find Q, which is the electric charge, we're going to plug in our equation here that we know, and then we're going to just set it to solve for Q, which is just some basic algebra, and then you're going to come out with this number right here, 1.401 times 10 to the negative 8th coulombs. And our number of electrons lost is equal to the charge of the tape over the magnitude of the charge of the electrons, which we know this number, we know this value. So boom, boom, easy calculation right there. And then the ratio of electrons to atoms is just the number of atoms over the number of electrons. Another easy calculation because we just found this. So there we go. So for every 4.57 times 10 to the 6 atoms, 1 electron was lost. So this is our Q amount that we need to solve for. And then into the coding, we're going to actually use this to find our magnitude of the force. So that's down here, the electric force on tape B. These numbers all do actually match with other calculations. This is just us plugging our constants and our initial values. These are the objects that we have tape B and tape A. This is our gravitational force, so electric force. We just put these equations in the code form, and then we use our electric field calculation to find the force. And that was pretty straightforward. So assumptions and sources of error for this is just air resistance and friction are negligible in calculations. The charge of both one is a point charge, so realistically it's not actually a point charge, but we're assuming it is. And then that they had evenly distributed charge. And our errors would be that there was no loss of charge due to handling of the tape, which we'll talk about in the next slide, and then we can ignore the impact of any other possible electric fields. So discussion questions for what if, let's say they switched charges, so electrons were now positive and protons were negative. This would change none of our observations or anything like that because like charges repel no matter what. So the pin would, in that case, instead of being negative, be positive. The tape would be negative. Tapes would still repel. They would still be attracted to the pin. And then why is it important to handle them as little as possible? Well, they start off neutral and we charge them. So they are losing electrons to become positive. When we handle them, they are gaining electrons back from the things that you touch them with. So if that's your hand, that's the floor, the table, the object you're taping it to, that's giving it electrons back, which is making it weaker. So the less we handle the tapes, the stronger the charge will be. Not even the stronger, just like the more accurate our calculations will actually be. So our conclusion is that electrically charged objects, in this case tape, have interactions with their object near them. We can predict this interaction using known variables and equations. In this case, we can measure the amount of electrons in the charge of a piece of tape based on how far it repelled another piece of tape that was also being impacted by gravity. And using code, we can model these interactions and compare them to our experimental findings. Thank you for watching.